Welcome back. This is the second video on section 4.1, in which I'm going to prove the symmetry of the second order derivative, if it exists. So, for the proof, we need a lemma which is similar to lemma 2.1. Okay, recall that lemma 2.1 states that if a linear map is a small o of the argument near the origin, then it is identically zero. And we have something similar if S is a bilinear map, okay, not necessarily on the same space, but we'll apply it for a bilinear map on a product of two identical spaces. So if the bilinear map is a small o of the square of the norm of H plus the norm of K, then S near zero, of course, then S vanishes identically. Now, of course, instead of norm of S, H plus norm of K, you can write the maximum, and of course you can replace it by norm of H squared plus norm of K squared if you like. And this is a norm here. Okay, so we prove that we don't need to assume that S is bounded, because it will follow that S is bounded. So we have to prove that S is bounded and its norm is less than any positive number. So let epsilon be given. This assumption precisely means that for hk small enough, less than a number delta, then the norm of S hk is less than epsilon times the square. Okay. So of course here we take the norm of hk to be the maximum, but you can take the plus if you like, or the Euclidean norm, doesn't matter. Okay. So now consider two arbitrary elements, h and k in E1 times E2, not necessarily small. If we multiply them by a small enough number t, then the norm of THTK will be less than delta. Okay. Why this is so? If h is 0 or k is 0, then any t would do. Okay. Or if both h and k are 0, then any t would do, because you get 0 less than delta. But if one of them is not empty, then it's enough to take t less than delta over the norm of hk. Okay, so according to the condition, the value of S at THTK, the norm, is less than epsilon times, so I just replace H by TH and K by TK. And now, using the homogeneity of the norm, I can put the T outside the norm here also, and then I can factor and raise to the power 2, so I get T squared here. And by homogeneity, double homogeneity of S, I can put the first T outside and the second T outside, so I get T squared, and I can put the T squared outside the norm. So, and then I simplify by T squared. And I get this inequality. And now this is true not only for hk small, it's true for all hk. Okay. So, in particular, if the norm of hk is less than 1, this is less than 4, so for epsilon. And this precisely means that S is bounded, and the norm of S is less than 4 epsilon. And since epsilon was arbitrary, we conclude that the norm of S is 0, and therefore S is 0. Okay, very simple. Now we go to the proof of proposition 4.1, which is a little bit tedious. Okay, but it's very important. The ideas and the techniques that we use here are really important in analysis. So introduce a new operator, a capital A of hk, and it's defined by f of a plus h plus k minus f of a plus h minus f of a plus k plus f of a, and you will see why I took this. Of course, this makes sense for hk near 0, because we need to ensure that a plus h and a plus k and h plus k all belong to U, to the domain of f. Okay. And this is possible if h and k are small enough, then the openness of U implies that all these arguments here belong to the domain of f. So there's no problem in the definition. So I can take hk as small as I wish. and observe that here H and K belong to the same set E. So when I interchange them, okay, instead of here I get K plus H, K, H. So we see that the map capital A is symmetric. And now we claim that this map minus the second derivative at hk is a small o of the norm of h plus the norm of k squared. Okay. So, and then the result will follow from the claim. So, but now this is not easy. So to do that, I will split this into two terms. So I will add and subtract minus f prime of a plus h in the direction k plus f prime of k. Okay. And then I use the triangle inequality. Okay, so now we would like to prove that each term is a small o of norm of h plus norm of k squared. The second term is easy to handle because by definition, of the operator norm. So I get f prime of a plus h in the direction k minus f prime of a in the direction k minus f prime of a in the direction h in the direction k. So I can factor by k if you like. So I get an operator. This is a linear operator now. And by the fundamental inequality linking the norm of a linear bound operator, we get that this is less than this quantity, the norm of this quantity times the norm of k, because I have k in common. Okay. And now the differentiability conditions of f prime at a means that I can find a positive number delta such that this norm, this is the operator norm actually, is less than is a small o of h. Okay, so it's less than epsilon norm of h if h is less or equal than a small number delta. Okay. And therefore, this second term is less than epsilon times norm of h times norm of k. Okay, if provided h is small enough. Now, to estimate the second term, which is more difficult, we introduce another new function, b of k, for fixed h, given by this formula, f of a plus h plus k minus f of a plus k minus the derivative at a plus h in the direction k plus the derivative at a in the direction k. And when I put k equals 0, I get f of a plus h minus f of a, and this is 0 because k is 0. And therefore, the first term, which is a of hk minus f prime of a plus hk plus f prime of k, is just bk minus b0, as you can check easily. Okay. Why did I write it in this way? Because, as you guess now, I will use the mean value theorem inequality. So bk minus b0 in norm for k small enough, okay, so that a plus k belongs to u. So it's less than norm of k plus the maximum of b prime, the derivative. So this is so on the straight line segment joining 0 to k. Okay, so I need to estimate this term. So I go back to the definition and I differentiate with respect to k. This is very easy. So I use the chain rule actually here. So it's f prime fixing everything, so fix h and fix a. So when you differentiate with respect to k, I get f prime of what is inside k times the derivative of k, okay, so which is 1 if you like, or okay. So it's f prime of a plus h plus k minus the same thing here. And now this term is linear and bounded in k, so its derivative, as you know from chapter 2, is just this linear map f prime of a plus h. And same thing for this one. So if you like, b prime k in the direction v is f prime of a plus h plus k in the direction v minus f prime of a plus k in the direction v minus f prime of a plus in the direction v plus f prime of a in the direction. Same thing. Okay. Now, so this quantity is actually a linear map from E into F. Therefore, when I replace K by Tk, I get this equality. And now this is the difficult part. I want to use the differentiability condition one more time, but for this I need to add and subtract similar terms. Okay, so first I add and subtract f prime of a. So I get minus f prime of a, minus minus plus, minus minus plus. So I get f prime of a, this cancels. F prime of a plus h plus tk is here. F prime of a plus tk is here with the minus sign. And now I use the linearity of the second order derivative. Okay, so f double prime of a at h plus tk is precisely f prime of a at h in the direction h plus f double prime of a in the direction tk. So these three terms cancelled actually. Okay, why did I do that? In order to use the differentiability condition of f prime at a. So now I take norm of h and norm of k both less than delta over 2. In this case, the norm of h plus tk is, by the triangle inequality, is less than the norm of h plus the norm of tk, which is less than the norm of k. So the sum is less than delta. Okay, so the norm of the increment here, if you like, is less than delta. So according to the differentiability condition, this difference is a small o of norm of h plus tk, which is less than this guy. Okay, so this is again the differentiability condition of f prime at a. And this is, by the way, the operator norm. It's not the norm in h, in f, capital F. It's the norm in L of e and f. And similarly, for the second term, because also norm of tk is less than delta, so I can write the same condition, and which is less than epsilon norm of k because t is less than 1. And similarly for the last term, okay. And now, if I, by the triangle inequality, just have to add these three, so I get 2 epsilon norm of h plus 2 epsilon norm of k, and I get this. Okay, and therefore, by the mean value theorem, I get 2 epsilon norm of h plus norm of k times norm of k. Remember the k because it comes from k minus 0. Okay, and this is of course less than, because norm of k is less than norm of k plus norm of h, so I get norm of h plus norm of k squared, right? So this concludes the estimate of the first term, which was a little bit difficult. But for the second term, we proved that it's less than epsilon norm of h times norm of k, which is of course less than epsilon times norm of h plus norm of k, everything squared, because if I square, I get norm of h squared plus norm of k squared plus twice the product. So of course this is bigger than this. And so by the triangle inequality, the norm of ahk minus the second order derivative in hk is less than 3 epsilon times this quantity. Okay, so since epsilon was arbitrary, this proves the claim. Okay, now we are almost done. Since h and k are arbitrary in E, we can interchange them. Okay, so when we replace h by k and k by h, we get akh minus f double prime of akh, and we get here same thing, norm of k plus norm of h squared. So these two guys are equal. So if I add these two inequalities and I use the triangle inequality, I get that the difference between these two guys is less than 6 epsilon times this norm. And now what is inside is, of course, for hk less than delta. So this means that this quantity is a small o of this norm squared. And by the lemma, because what is inside is a bilinear map, so it means that what is inside is 0, is identically 0. So I can write f double prime of a in the direction hk minus f double prime of a in the direction kh is 0. And this is true not only for hk small, it's true for every hk. So if you like, we can write f double prime at a in the direction uv minus the same thing vu is 0 for all uv in E. Okay. And that's it. So this concludes the proof of proposition 4.1. Now, as an exercise, I want to revisit the case of a map of n variables. So suppose that we have a map of n variables, which is twice Frechet differentiable at the point A. then we have to show that this double sum of the mixed partial derivative is equal to the same thing with arguments interchanged. Okay. And we have to deduce from this that this following inequality between mixed partial derivatives. So the second order derivative with respect to xa and xj. So xi first, xj second, at a in the direction of vu is the same thing, but we flip. So we flip the order of differentiation, and we flip the order of the arguments as well. Okay. You have to deduce this from this actually by a particular choice of hi and kj. Okay, and now in particular, you will prove that a generalization of Schwarz theorem about the equality of mixed partial derivatives. Okay, it's also known as Clairaut theorem that you probably studied in calculus. But usually in calculus, you prove it under stronger assumptions that f is of class C2 or that the mixed partial derivatives are continuous. But here we don't need to assume that. All we need to do is that f is twice differentiable at one point. Okay, then the mixed part, but of course here we have some restrictions. So we have, so all the variables belong to the same space R. So, right? So f is a function of n real variables that takes values in an arbitrary normal space. Okay. Usually we prove this for a function of n variables into R. Okay. But here we can do this generalization. Okay. Okay. And there's a challenging question actually. Is the mixed partial derivative usually symmetric in general? Note that if you think of this problem, you will see that the symmetry, if this is symmetric, then I can interchange u and v, and I get the same argument uv here, and therefore they get that the mixed partial derivatives are equal. And conversely, if the mixed partial derivatives are equal, then each one of them is symmetric actually. So it's equivalent. But is that true in general? If yes, prove it. We proved it actually in a particular case. Okay. If not, then you have to give a counterexample. Okay. But this is a little bit challenging. Okay. And it's rather a deep question actually. It's a research question. Okay, so this concludes this video on the second part of section 4.2. In the next video, I'm going to move to higher order derivatives but don't move to higher order derivatives if you didn't understand the second order derivative case first. Okay. So thank you for your attention and see you next time.